So today we are going to talk about subspaces. A non-empty, so this notation means non-empty. Different from empty set means non-empty. This means a subset. So a non-empty subset of a vector space V is a subspace if itself is also a vector space. You will have to check on 10 properties and see if W really satisfies the 10 properties to be a vector space or not. That's a lot of work, of course. The interesting thing is that we actually don't have to test all 10 properties. We actually only have to test A and B, which is property number 1 and property number 6 if you compare them. All right. Property number 1 says that if you start with two vectors from the subset and you add them, then the addition will give you another vector or another element, because we have not yet known if this is a vector space, so we should call them the elements. The addition will give you the another element that is also in W. And property B is actually property 6. If you start with an element in W, the smaller subset, and R is a real number, then when you scalarly multiply R to the element A of W, this is going to give you something new. Of course, this is going to be in V, right? Because that's the biggest space that contains W. This is going to be in V, but whether it is still in W, the smaller subset or not, it depends on the type of the smaller subset that you started with. Now, if the smaller subset W satisfies the two special properties here, you don't have to check the other 8 properties. It will automatically become a sub-vector space of the big vector space V. So literally, this theorem says that the 10 properties from 1 to 10 in the definition of a vector space, in this case, for the subset W, the non-empty subset W, the 10 properties is equivalent with the 2 properties, 1 and 6. Right. If we check this property, which is property number 1, A is 1, right? And it's satisfied, then we say that W is closed under the addition. Because you start with something inside W, you add them, and you still being inside W. So you are not going outside if you just add. That means it is closed with the addition. And similarly, if you test B, which is property number 6, we say that this is closed under the scalar multiplication. So the only thing that we require a subset to be a subspace is that it is closed under the addition and the scalar multiplication. The other 8 properties can be proven easily. Right? How can you prove that from 1 and 6 you automatically have 2? Well, that is because if you start with A and B being in W, the fact is that W is a subset of V implies that A and B are in V. And because the addition that we are using on W is the same as the addition that we use in V, so this turns out to be the addition in V. Because A is an element in V, a vector in V. B is a vector in V. So when you add them, you are adding 2 vectors in V. And because the addition in V is commutative. Why? Because V itself is a vector space, right? The V is the big vector space that we were given. So the addition on V in V has been already commutative. So that means that you will have to get E equals B plus A for granted, because the addition in V is commutative. So in other words, because W is inheriting the addition and the scalar multiplication from V, so all these properties will be easily proven, just like what I did here. Right. The only things left that we worry about is this property and this property. Now, why am I worrying about the property number 4 and the property number 5? Say property number 4 first. That is because I am not sure if the vector that plays the role of the zero vector in W is the same as the vector that plays the role of the zero vector in V. All right, we even haven't known yet the zero vector in the bigger space is still in the subset or not. For example, in R2 is a vector space. And it will play the role of V. Right. Now you consider a smaller subset, W. You know that this is the vector 0 where it is located. But you see that being a subset doesn't mean it has to contain the zero vector in V. Right? So the zero vector in V may not be inside W. And so I will have to search for another thing that will play the role of the zero vector for W. Otherwise, property number 4 will not be satisfied, and it cannot be a vector space if we cannot find such zero vectors. So that's the idea. So now I'm going to prove that the zero vector in W really exists, and furthermore, is in fact the zero vector in V as well. Non-empty is very important. Right? Anything that we define, we want it to be correct on a non-empty set. Otherwise, what's the point to do that? You are working on something empty. Literally, you don't have anything to work on, right? So it has to be non-empty first. And as I said, so I'm going to prove that if W is non-empty and W satisfies A and B, then W satisfies property number 4. Furthermore, the 0 in W turns out to be the 0 in V as well. First, I am going to prove that the zero vector in V has to be in W. Now, if you are only given a non-empty subset of V, there is nothing for sure that zero vector in V has to be in that non-empty subset. But because this non-empty subset is very special, it has the two properties A and B, right? So we can prove that. Because W is not an empty set, so there must be an element, say W0 in W. Now, because W satisfies property B, right, which says that it is closed under the scalar multiplication, this implies that -1 times W0 is inside W. In other words, the negative vectors of W0 is inside the subset capital W. We have already had some whole assignment proving that -1 times a vector is going to be the opposite of that vector. So that opposite vector, which was initially in V, now will have to be in the smaller set W. Now we utilize the fact that W satisfies property A closed under the addition. That means if we add W0, a vector in W, with negative W0, another vector in W, we will end up having something inside W. But what is this? This guy, when you add two vectors opposite, the negative, this is going to be the zero vector. But wait a minute, is this the zero vector of V or the zero vector of W? This is the zero vector of V, right? Because this is in W, but W is a subset of V, so this is in fact in V. Similar, this is in W, and W is a subset of V, so negative W0 is in V, of course. What is the addition here? This is the addition in V. And so if you add two opposite vectors in the vector space V, the big vector space, by the addition in the vector space V, you will end up having the zero vector inside V, right? Add two opposite vectors, you get zero of the vector space. All right, so that's good because we have already proven that the zero vector in V now has to be in W. Now this is key because now if we want to prove that 0W is in fact the same as 0V, we actually just need to show that we add this newly found vector in W with anything in W that will preserve the thing that you are adding to it. All right, so now we'll prove that this zero vector in V now in W has to satisfy or act as the zero vector for W. For any element A in W, we have this A is in W, and W is a subset of the bigger thing that is V. This is the zero vector for V, and this is the addition that is the same as the addition in V, so it's actually the addition in V. Right? The addition in W is actually just inherited from V, so fair to say. Now you add some vector in V with the zero vector of V, of course you have to get A by the fourth property for the vector space V. All right, and this is true for any A. Well, that means that this guy, which we have known to be also in W, will act as if it is the zero vector for W, because you add anything in W, you end up getting the same thing. So we write the zero vector for W is the same as the zero vector for V. All right, and so we have proven property number 4 for W. All right, once you have the existence of the zero vector, then proving property number 5, the existence of the opposite vector, is going to be simple and it's pretty much similar. So I'm going to leave the proof of property number 5 for you to try. So next, here are several more examples of a vector subspace, right, or subspace in short. So this notation, the C stands for the word continuous. So this is the collection of all continuous functions on the closed interval from A to B. This is in fact a subspace of the space of all real value functions defined on AB. Why? Because if you start with two continuous functions and you add them, you will end up having a continuous function. If you multiply a continuous function with a number, which is the scalar multiplication in this case, you also end up having another function that is continuous. So this collection of all continuous functions is in fact closed under the addition and closed under the scalar multiplication, which are the properties A and B. So it is the subspace of FAB. Right. And we know these facts because of what we have learned from calculus 1. Right. Span. Right. Often we are going to work with the collection of some given vectors. Say here we are given k vectors. Then we are going to use k numbers, k real numbers. We multiply the first number with the first vector, the second number with the second vector, the last number with the last vector, and we add those together. This form is called the linear combination of A1, A2, and up to AK. The collection or the set of all linear combinations that can be formed from the k vectors is denoted as span of the k vectors. And the span of the k vectors is in fact a subspace of the bigger space that we started with. All right, so that's the properties that we are going to prove. We note it as star. Now the fact is that this is an interesting fact. If one of the vectors in the spanning set is a linear combination of the others, then you can throw that one out, use the rest to span the space, and you end up having the same thing. In other words, any vector that is a linear combination of the others is useless vector in the spanning set. Now this is going to be the proof for star. In this case, W is the span of A1, A2, dot, 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 AK. All right. We have to prove that this satisfies property A and property B. Note that W is non-empty because if you write any of them here as 1 times itself and then plus 0 times the others, then this is, by definition of linear combination, this is a linear combination of the k vectors that we were given. And if it is the linear combination of the k vectors that we were given, it has to be in the span of the k vector by definition of what it means by the span. And from now on, I'm going to just write W to save us time. So now we are working on some set that really has something to play with. Now we have to prove that W satisfies A. In order to prove that, we have to start with any arbitrary A and B in W. We need to show that A plus B is also in W. A is in W. That implies that A is a linear combination of A1, A2 up to AK. That means A will be equal to R1, A1, R2, A2 plus RK, AK for some real numbers. R1, R2, dot, 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 RK. We don't know what they are, but there must be some real numbers that will make the combination 5. Right. Similarly, base is in W, so there must be some other real number S such that B equals to S1A1 plus S2A2 plus dot, dot, dot plus SKAK for some real numbers s1, s2, dot dot dot, sk. We are using s instead of r because we'll never know if b is exactly equals to a or not. We just start with something very random, very general. So we keep things the most general. Now, we have already identified how a looks like and how b looks like. Next, we are going to add them and see if the result is still in w, right? So we are going to add a and b. Now, if you add a and b pairwise, then you can group them because the scalar multiplication and the addition in a vector space, which is in V, right? V is the big vector space. You have the distributive properties. You will have R1 plus S1, A1, R2 plus S2 times A2, RK plus SK times AK. Now look, this, this, and this. They are all real numbers. All right. That means you are multiplying A1 with a real number, A2 with a real number, AK with a real number, and you add them all. What is it? It's a linear combination of A1, A2, and AK, right? And if it is a linear combination of A1, A2, and AK, that means that A plus B is inside the spanning space of these vectors. So this implies that W satisfies property A in the theorem. Similarly, we can prove that W satisfies B close under the scalar multiplication, right? And I'm going to leave this for you as an exercise. Try to mimic what I did and write something on your own, right? Make it nice as possible. That's the first step. You learn how to write a proof. And so because W satisfies A and B by the theorem, W is, what is W, right? I want to remind you that W, which is the span of A1, A2, AK, is a subspace of V. And that's it. I would like to discuss a little bit about the fact here. This fact. All right, so now A1 is a linear combination of the orders. That means you can write A1 as R2A2 up to RKAK for some real numbers R2 dot 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 RK. Of course, if you span from less vector, you will expect something smaller, right? Because anything from here will have the form x2a2 plus dot 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 plus xkak. I'm not using r to avoid the confusion with the a1 here, right? So I'm using other notations here. But this is the same as 0 times a1 plus x2a2 plus dot 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 plus xkak. So a linear combination of fewer vectors can always be rewritten as a linear combination of more vectors. So this is checked. Now, if you consider the span of more vectors, How can you prove that it is contained inside the span of fewer vectors? That's the hard thing to prove. Now, luckily, we can do that because A1 is a linear combination of the orders. We start with anything from here. We will prove that this anything will end up being in this one, or in other words, any combination of A1 up to AK will turn out to be a combination of just A2 up to AK. Let's say any A from here. A will be a linear combination of S1, A1, and I'm using different notation than R to avoid confusion. S2, A2 plus SK, AK. Then this is S1 times A1 is the combination of the orders. Right? So we substitute it with the combination that we wrote down at the beginning. All right, and then actually you just distribute this S1 into the sum, right? You can do that because it's the vector subspace already. So we actually are going to pair this one with this one because they are multiplying with the same A2, and you are going to pair the last with the last. Eventually, what you end up having is that you are able to represent vector A as just the combination of A2, AK. And so it has to be in the span of fewer vectors here. You can do that at home, I believe. Try to distribute and rearrange terms so that you can see that A is in fact just some number times A2 plus dot 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 plus some number times AK. And it is in the span of fewer vectors.